over the next few weeks. I actually got my PhD at Michigan in 2016, and my thesis topic was these symmetric Playback graphs. So what happens to Playback graphs if you impose a symmetry condition? Playback graphs being these planar bicolored graphs introduced by Postnikov. We got just a preview of those at the end of the last talk, and we'll see more of them in the next hour. So today I'm going to circle back to that project, talk about some progress that I've made on it recently, and also kind of where things stand now, what some problems might be for anyone interested in picking up the torch and taking this one step further. So to get started, I'm going to give a very broad strokes overview of Playback graphs. There's no way for me to do this at all the justice it deserves, but I'll say enough to hopefully make the talk intelligible. We'll talk about weakly separated collections, which came up briefly during the Q&A and during the last talk, and about this really powerful theorem that ties weakly separated collections and Playback graphs, proved by David Speyer, Suho Oh, and Alex Postnikov. And then I'll go over symmetric Playback graphs, which are Playback graphs, again, with just a very elementary symmetry condition overlaid. Talk about how those can be kind of interpreted algebraically, geometrically, and introduce a symmetric notion of weak separation. And we'll tell a symmetric version of the story linking weakly separated collections and Playback graphs. And I'll end with some pictures that give kind of an idea of the proof ingredient and maybe a better idea of the structure of symmetric weakly separated collections. So I'm not going to prove anything, but I'll give you some ideas, some ingredients. So let's start with a quick overview, as I said, of Playback graphs. So Playback graph is a portmanteau of planar bicolored. So these are networks that are planar, embedded in a disk, vertices are colored black or white. And these were introduced by Postnikov in the, I believe, early 2000s, and they give coordinate charts on the Grassmannian, on the variety whose points are in one-to-one correspondence with k-dimensional subspaces of an m-dimensional space. These are, as we saw in the last talk, related to total positivity, as well as to cluster algebras. I'll say a little bit more about that later on. And again, as we started to see in the last talk, there are many, many ways to think combinatorially about how do you start with one of these bicolored networks and end up with a coordinate chart on a Grassmannian. So we have Postnikov's original construction, counting weighted paths in directed networks. And then this evolved into a recipe using dimers or almost perfect matchings, which I think is first explicitly spelled out in some lecture notes of Thomas Lamb, but building very much on work of Kelly Teleska, as well as Postnikov, Speyer, and Williams. And then another formulation that will be the focus in this talk is assigning labels to the faces of Playback graphs and thinking of those face weights as representing minors of a matrix. So that's the formulation that we'll talk about today. In my thesis, I talked about almost perfect matchings of symmetric Playback graphs, but translating it to the language of face labels wasn't quite ready. So how do we label the faces of a Playback graph? We're going to use these zigzag paths, or trips, that are defined using Postnikov's rules of the road. So we start at the boundary of the graph, we turn right at each black vertex, and left at each white vertex, and when we hit the boundary again, we stop. And then there are many ways to do this, but our convention is we will label a face with index I, so in the example with a 1, if it is to the left of the trip ending at I, so ending at 1. So here we have 3 faces that pick up a 1. By the way, I will not go into this at all in this talk, but not any planar bicolored network is considered a legitimate Plabic graph. There are some technical conditions that these networks have to satisfy, and those can be expressed by looking at these trips and making sure that they don't kind of intersect in redundant or messy ways. If I repeat this process with all possible trips in the Plabic graph, which I've done here, one thing that we can notice is that every face picks up the same number of indices, of labels. So here, each face is labeled with a pair, 1, 2, 2, 3, 1, 3, and so on. And so this is going to give you a coordinate chart, a set of rational coordinates on a Grassmannian of k-planes in M space, where here M is the number of labeled boundary vertices, and k is the number of integers in each face label. Okay, so that's the combinatorial recipe of labeling faces. And now I'd like to think of those face labels as coming from minors of a matrix, in this case, a 2x4 matrix. So we can represent the Grassmannian of k-planes in M space, 2 planes in 4 space, by full rank k by m matrices modulo row operations. To keep things one-to-one and kind of capture that modulo row operations, here, I'm assuming that all of my 2x2 minors are non-zero, and I'm going to just declare by fiat that the minor corresponding to the first 2 columns is 1. Declare that by fiat, and then I'm going to carefully fill in this matrix so that if I take, for example, the 2x2 minor that I get by selecting columns 1 and 3, that gives me the face weight that appears here on the face labeled 1, 3. Here I've gone ahead and worked out all of the minors of this matrix. The only one that you can't read off directly from the graph is the one that you get by taking column 2 and 4 of the matrix. And reading off from the matrix here, I'm getting C plus BD over A. The actual formula here is maybe a little less interesting to me right now than just noting that if A, B, C, and D are all positive real numbers, this last minor, 2, 4, which is uniquely determined by the ones that we've expressed as face weights, is also going to be positive. So we're starting to see that connection to total positivity that was mentioned in the last talk, that forcing the minors corresponding to these face weights to be positive forces all of the maximal minors of this matrix to be positive. So that's a very small example, but this is, of course, a much bigger story. In general, if we restrict to positive weights, we get an isomorphism to the totally positive part of the Grassmannian, so the part corresponding to matrices where all maximal k by k minors are positive. And the minors indexed by face labels of a Plabic graph form clusters in a cluster algebra structure on the coordinate ring of the Grassmannian. In particular, these minors form a total positivity test, there's a typo, for the Grassmannian of k-planes in M space, that if you want to know if a point in this Grassmannian is totally positive, you can get away with only checking the subset of maximal minors that correspond to the set of face labels of some Plabic graph. If those are positive, you're good. The others have to be positive as well.
The question, is N the same as M?
Yes, that's a typo. I have an ulterior motive for using M as my ambient space, which is that N is going to have another job later, but I'm very conditioned to write GRKN, so that's on me. Thanks for the clarification. Okay, so that is my very brief overview of just enough Plabic graphs to state my theorem. Now, I will say there's a much more elaborate story here where we can decompose the Grassmannian into subvarieties called positroids, and every positroid can be parameterized by Playbit graphs, and this stratification has a beautiful combinatorial structure, plays very nicely with total positivity and total non-negativity. So everything that I'm going to be stating in this talk also holds in that broader context. So I'm not going to talk about smaller positroids just for the sake of having clean theorem statements or minimizing notation, but for positroid experts, everything I'm saying there works in that context. All right. So now I'd like to briefly review weakly separated collections, which I know were discussed a bit in the last talk. So we say that two k-element subsets of this notation bracket m is going to mean the set of integers 1, 2, up to m are weakly separated if, when your larger set 1 through m is arranged around a circle, there is a chord that separates the complement of j in I from the complement of I in j. So here's an example. I will often denote k-element subsets of some larger bracket m by going ahead and putting my integers around a circle and then putting a dot for each element of the set. So here I'm looking at upper left, I have 1, 4, 7, 8. And then here my second, in this case, 4 element set is 3, 4, 6, 7. And I see that I can draw this chord, and here I have elements that are contained in I but not j. Here I have things contained in j but not I. Since 7 is contained in both, it doesn't factor into this picture at all. Since 2 is contained in neither, it doesn't factor in at all, and so on. And then here's just an example of two sets that are not weakly separated from each other. You can see that if you traverse the circle, you see elements of I but not j, and elements of j but not I kind of interleaved, so there's no way to separate them by a chord of the circle. And when we say a weakly separated collection, we mean a set of a collection of k-element subsets of bracket m, which has the property that any two members of the set are weakly separated from each other. So there's no kind of global property where we have to put everyone around the same circle. It's just any two elements play nicely with each other. So now, what does this have to do with Playbit graphs? Well, J.S. Scott, in the paper Grassmannians and cluster algebras, showed that the face labels of a Playbit graph are always going to be a weakly separated collection, which is maximal by inclusion. You can't add more elements to it and get something that is still weakly separated. And also that a weakly separated collection of k elements in bracket m, it's always going to have size less than this formula in m and k, which coincides with the number of vertices in one of our kind of allowed Playbit graphs. Based on this, he made what I'm going to call the purity conjecture, which is that a weakly separated collection of k-element subsets of bracket m is maximal by inclusion among all such weakly separated collections, if and only if it's maximal by size. So if you have any weakly separated collection that is not maximal by size, you can keep adding things to it until you hit that upper bound. This is related to an earlier conjecture of a very similar flavor by Leclerc and Zelevinsky. They were looking at a slightly more expansive notion of weakly separated sets that lets you compare two sets of the same size. But they made a conjecture very much of this form. And here Scott kind of adapted it, I would say, more for the Playbit graph context. That's my understanding of the story. If I'm mixing this up, please feel free to let me know. This was proved by Postnikov, Owen, Spire in the, I believe this paper appeared in the chat in the last talk. And I hope that we'll hear more about Playbit tilings later on. Because I won't have time to fully go into that construction here, but using Playbit tilings, these black and white tilings that are dual to Playbit graphs that they invented, they were able to prove this really powerful theorem that actually implies both Scott's conjecture and the earlier conjecture of Leclerc and Zelevinsky, which is that for a weakly separated collection, all of these things are equivalent. It's maximal by inclusion, so you can't throw in another element that's weakly separated from everything there. It is maximal by size, it hits that upper bound, and it is the set of face labels of a Playbit graph, which gives rational coordinates on the Grassmannian of K-planes and namespace. All of those are equivalent. So that is the story so far. And then in the remainder of this talk, I'm going to circle back to some earlier constructions for my thesis and use them to tell a symmetric version of the story, to say, what if, can we tell the same story?
Can I make a little comment? Like,
please do.
About the purity conjecture, around the same time, it was also independently proved by Danilov, Karzanov, Koshevoy.
Oh, thank you. Yes, I really should have them on the slide. We'll hear a bit more about some of their work later on, but yes, thank you. Mm-hmm. They deserve a citation here, absolutely. So let's take a quick look now at these symmetric Playbit graphs. So the idea here is that we say a Playbit graph is symmetric if when you reflect across the vertical axis, you preserve the underlying network, but flip the colors of vertices. In particular, this means you're not allowed to have a vertex right on the midline, because what would you do with it, right? You can't, it would have to be sort of simultaneously black and white. And then we're also going to put a constraint that a face and its mirror image have the same weight. So here I've gone ahead and redone our matrix. So we have the same graph. The graph is already symmetric, and the only thing I've changed is that instead of having a fourth weight D, I now have a B. So I'm only parameterizing a three-dimensional thing. The kind of yoga of why I was interested or motivated to do this is that in the Grassmannian case, we have all of these beautiful type A combinatorial objects, of which Playbit graphs are only one. And kind of the yoga here is that if I impose the right kind of symmetry on a type A combinatorial object, maybe I will get kind of a type C version of the same story, or a type B version of the same story. A parallel version in a different type for a relative of the Grassmannian. And that does work out here. It turns out that imposing symmetry on the graph means that you're restricting to matrices whose rows are orthogonal with respect to a skew symmetric bilinear form. In order for this to work out, all my signs to end up as I need them to be, I have to set this up a little bit carefully. So we're not going to use the details of this later, but just for concreteness, what's happening here is I will define a bilinear form by taking the standard basis in a 2n dimensional space, and I match up EI and EJ and say they are -1 to the j if I plus j is 2n plus 1, and otherwise 0. So it's a little bit of a funny form to use, but it gives us exactly what we need. So for example, here's the matrix from our last slide. I'd like to make the case that the rows of this matrix are orthogonal with respect to this form. And indeed, if I take the product, I have 1 times b, and then because of these alternating signs, -0 times a, plus -b times 1, minus -c plus b squared over a times 0. So a little messy, but this quite clearly boils down to b minus b. So by imposing a symmetry on the network, or by insisting that the network have a certain symmetry and then imposing some relations on the weights, I was able to restrict to matrices where the rows are orthogonal with respect to this form. I'm going to denote by this capital lambda the subvariety of the Grassmannian, whose the Grassmannian of n planes in 2n space, so 2 planes in 4 space, for example, corresponding to maximal isotropic subspaces with respect to the bilinear form defined. or more concretely, points represented by matrices whose rows, again, are orthogonal. And morally, the main theorem of my thesis was that these symmetric Playbit graphs give coordinate charts on the Lagrangian Grassmannian kind of in much the same way that Playbit graphs give coordinate charts on the ordinary Grassmannian, and that many of the really beautiful combinatorial results for ordinary Playbit graphs import nicely to the symmetric case. But one thing I was not able to address at that time was this base labeled story. So a little bit of an update using both those earlier results and also work of Muller and Spire. We can do the face label construction, and it plays nicely, as we saw in the example, with imposing symmetry and looking for orthogonal rows. Okay. So now that we know that we can talk about face labels for symmetric Playbit graphs and that that has some geometric meaning, I'd like to characterize the collections of face labels that I can get. I would like that to have some analog of the purity conjecture. And this does indeed go through quite nicely, although there's quite a bit to check as well. But first we need the right notion of symmetry. So just a little bit of notation. I have a fixed n that I'm using for the rest of the slide for any integer from 1 up to 2n. So for any I bar is just the integer such that I plus I bar equals 2n plus 1. And then I apologize for this notation. If I have an n element set I, bar of capital I does not mean take bar of every element of capital I. It means take the complement of that in the set of integers from 1 up to 2n. So I hope that is not too counterintuitive. So just as a quick example, I have here n equals 3, so 2n equals 6. Capital I, my set is 2, 4, 5. To get what I'm going to call the reflection of capital I take the set of integers 1 through 6. Since 2 was in I have to knock out 2 bar, or 5. Since 4 was in I have to knock out 3. Since 5 was in I knock out 2, and I'm left with 1, 4, 6. I'll say that a weakly separated collection is symmetric if, for any element of the set, I also contain its reflection. So for any element of for any set in the collection, I also contain its reflection. Hopefully that's clear. And with this notion in place, as I said, we get kind of a complete analog of the theorem from a few slides ago. So we have an equivalence between being a symmetric weakly separated collection, which is maximal by size among all such collections, a collection being maximal by inclusion among all symmetric weakly separated collections, so not contained in a larger collection which checks all of those boxes. And that's in turn equivalent to being the set of face labels of a symmetric Playbit graph. So this is not obvious, because if I have a weakly separated collection that is symmetric but not maximal, I know that I can add more elements and turn it into a full weakly separated collection, turn it into a set of face labels for some Playbit graph, but it's not a priori guaranteed that I'll be able to preserve symmetry as I do that. And what this theorem says is yes, I will never get to a place where I've kind of filled in most of my graph, and the only way to take it to the finish line is to break the symmetry that I want. And then I was very excited to see on the archive just a few weeks ago that the equivalence 1 to 2, a symmetric weakly separated collection being maximal by size, if and only if it is maximal by inclusion, has actually been generalized by the team that also independently proved the purity conjecture. So Danilov, Karzanov, and Kosherboy, they have a generalization of this equivalence that encompasses a more expansive notion, again, of weak separation, where you can compare sets of different sizes. And also, they've keeping a similar notion of symmetry, but they've expanded this to some other types of separation relationships. So if anything in this talk is interesting, I strongly encourage checking out that preprint. Like I said, hot off the press from early this month. Okay, so in my last few minutes, what I'd like to do is, as I said, give a flavor of why this notion of symmetry is the right one, how to make this a little bit more visual, and what it tells us about kind of the structure of symmetric weakly separated collections, how we can think of those in terms of total positivity tests and coordinate checks. Okay. So here I have a symmetric playback graph. We're in the case where n equals 3 to n equals 6. And I've highlighted two trips in the graph, one that ends at 1, one that ends in 6. We can see that the notion of symmetry that we have on the graph means that for any trip, the mirror image is also a trip, right? Because reflecting the graph switches the colors of vertices, we get the mirror image of this directed path also following the rules of the road. And we can see from this picture that a face is to the left of a trip ending at 1, if and only if its reflection is to the right of the trip ending at 6. So a face label contains 1 if and only if its mirror image does not contain 1 bar, does not contain 6. So that's where that somewhat counterintuitive definition of reflecting a face label comes from. And that tells you right away that surely the face labels of a playback graph follow this idea of symmetry. The tricky part, again, is showing that you can go the other way, that you can take a weakly separated collection that has this symmetry and fill it in without breaking symmetry at some point. And now let's talk a little bit about, again, some proof ingredients. By the way, if you're looking at my lower right corner, because I know I do this sometimes, I don't actually have 24 slides. There's some bonus figures and references at the end. I really just have a few more things that I wanted to show you. So I'd like to talk about how we can tell from looking at a face label and without drawing a picture, just on a purely combinatorial level, where it's going to land in a symmetric playback graph, whether it will end up on the left, right, or center of the graph, and also about which face labels can potentially appear in a symmetric playback graph and which ones can never appear at all. So the idea is, again, I'm pairing integers with kind of their opposites as I reflect these diagrams vertically. So in this case, I'm looking at integers 1 through 8, and I'm going to pair up 1 with 8, 2 with 7, and so on. So you have a full pair in a face label if you have both an integer and its partner. So here we have a full pair at 1, 8. Here we have a full pair at 3, 6. And then empty pairs are analogous to that, right? We have an empty pair at 3, 6, and an empty pair at 1, 8. And we get when we reflect a face label, if we think in terms of this visual representation, what we're really doing is exchanging full pairs and empty pairs, right? If I reflect an element that contains both 1 and 8, well, since it contains 1, its reflection can't contain 8, and since it contains 8, its reflection can't contain 1, and so on. So to be a face label of a symmetric playback graph, or to live in a symmetric weakly separated collection, you had better be weakly separated from your own reflection, right? That is clearly true. We call elements that kind of follow that rule admissible. And from the discussion on that last slide, what it means to be admissible, what it means to be weakly separated from your own reflection, is that if we do one of these visual representations and we scan from top to bottom, you have to either have all of your full pairs above all of your empty pairs, or vice versa. Here we have an example where if you kind of scroll from top to bottom, you get full, empty, empty, full. And you can see that this is not weakly separated from its reflection. Right, if I interchange full and empty pairs, I get something that is not weakly separated from what I started out with. So possible elements of a symmetric weakly separated collection have to follow this rule that you can't have full and empty pairs alternating as you scan from top to bottom. Based on this, we can classify face labels and tell where they're going to land on a graph kind of automatically. If, as you scan from top to bottom, you get full pairs above empty pairs, that's going to land on the left side of your graph. If you get empty pairs over full pairs, that'll land on the right. And here we can see 1, 6, 4 is on the left side of the graph, 2, 4, 5 is on the right. And then the elements that don't have full or empty pairs anywhere, those land right on the center because those don't change when you reflect them. So why is this interesting? Well, the proof here that you can complete any symmetric weakly separated collection to one of maximal size, that is the face labels of a playback graph, is you first prove that no matter what your collection looks like, you can add center elements to fill in kind of a chain down the middle. Once you do that, and that's a little bit hard to prove, but once you do that, you can fill in left and right elements in pairs pretty easily. The fact that you have this chain in the middle kind of forces a situation where it is safe to fill in, say, one side of the graph, and then just do the mirror image of everything you've done on the other. The other thing that this way of thinking about face labels does is that it makes it a little cleaner to talk about coordinate charts from these symmetric weakly separated collections. So if I have a maximal symmetric weakly separated collection that I built sort of combinatorially, maybe without a lot of reference to a graph or tiling, I can tell by examining individual elements whether they are left, center, or right. If I take just, for example, the left and center elements only, those are going to give me a coordinate chart, right? The entire set doesn't. The entire set is at this redundancy because I've imposed some relations on the weights of my graph. But I can grab a set of coordinates by looking just at left and center elements. And those will give kind of a nice minimal total positivity test on matrices that are isotropic with respect to this form. So the combinatorial story of total positivity and playback networks, again, is carrying over really, really nicely, I would say, to this symmetric situation. But of course, the thing that looking at this you would want to be true, and that I want to be true, and I think in some form is true, is that these should be giving you cluster variables in some kind of cluster algebra structure. And that's something that I still don't know what the answer is there, how to make that happen. I haven't had a lot of kind of space in my research life to get around to that, but I know that there are likely folks at this conference who are sort of getting into this area. And so I could offer that as a problem. If this is something that is of interest or that you'd like to work on or talk to me about, I would definitely love to hear from anyone who is on that team. So that's all I have for now. There are a couple of just bonus figures that I can show if it would be helpful to have more bigger examples, but I'm going to stop there. Thank you so much for listening. I have not been able to monitor the chat, but I would be very happy if there's any questions to to answer those as well.
Okay, there have already been some interesting questions and